Hello friends, welcome to follow up. In this video, we are going to look at problem 3045, count prefix and suffix pairs 2. In this video, we are going to explain how we can use trie data structure, also known as prefix tree, to address the very problem here. So notice that in leetcode, there's another problem. It's called count prefix and suffix pairs 1. So due to the small size of that problem, so basically we can use brute force to solve that one. But here, so this is the core problem. So our plan will be the following. So we are going to implement a trie partially, I would say, and then we will address this problem. So the problem here says that we are given a string, we're given an array of strings, right, called words. So basically we want to define a Boolean function. So it's called is prefix and suffix. So it takes two strings, string 1 and string 2. So we want to return true if string 1 is both a prefix and a suffix of string 2, otherwise false. For example, ABA here is both a prefix, because here we have ABA. Also, ABA here is also suffix, right? So this will be true. Well, if you look at ABC and ABCD, so this is ABC is a prefix but not a suffix, therefore we return false. So this is the functionality here we want to have, right? So the overall purpose is to return an integer denoting the number of index pairs, Cij, such that I is before G, and the corresponding string at index I is both a prefix and a suffix for the string at index G, right? So here we have several examples. So example 3 is very special. It just returns 0, right? Because this one is longer than the second one. Well, you look at example 1. So the output is 4. So we can start from this one, because this one, they have some previous ones. So here, if you look at A, right? A is both a prefix and a suffix of ABA. And also, if you look at A and this one, and because it starts with A and ends with A, so it's also a both a prefix and suffix. We have another pair. So similar for this one. So this A contributes 3 pairs, right? So if we look at ABA, and then we look at this one, so ABA is both a prefix and a suffix for this string at index 2. So therefore, it contributes another pair, that is pair 1, 2, right? However, it's not with respect to the string at index 3, because this one has length 3 and this one has length 2. So it's impossible to form prefix and or suffix relation. And if you look at this one with respect to the two A's, it also cannot, because the length is longer. So this is the 4, right? So if you look at the constraints for this problem, the word length can be as long as 10 to the power 5. Well, each word itself can be also up to this length, and therefore we cannot do a very brute force one to check every pairs, right? That's actually n square term complexity, not mentioning that each word can be as long as 10 to the power 5. So this is the first two assumptions or constraints. So if you look at word I, so it consists only lowercase English letters. So this is a good thing, right? It's roughly restrict the problem size, because we could have essentially uppercase and other ASCII letters or Unicodes. So here the number of lengths of all words does not the sum, right, does not exceed this one. It's also a constraint of problem size. So if you look at this problem, and if you want to do it manually or just digest that, it's rather straightforward. Well, if you do a implementation which is very efficient, that's not very trivial. So here, this is some hint, right? So you can use trie. So you should have this intuition if you have practiced a number of problems in leetcode or do some other coding practices. So then the thing is, how could we use trie, right? So here it processes all words I from left to right. So the trie starts the pairs. So like this, it's not very clear, but we want to use each word's pair, right? So here, during the insertion, it keep a counter in each trie node, as in a normal trie, right? So this is the actually the counter will be specific to the problem logic or to our goal, because we want to find the matching pairs. So the thing is that we are not interested in the specific pairs, like which pair, like 1, 2 or 1, 3. We are interested in the counting, right? So that's the part. And the last hint, let's see. From left to right, insert each word into the trie and increase our final result by each node's counter, right? When going down in the trie during the insertion. So this means that there were at least one word that is both a prefix and a suffix. So notice that the problem also assumes that we want the pair to be like this, I and J. I is in the left of J. So in other words, when we do the insertion, we just need to insert from left to right. So this is very natural, right? So let me first recall for the typical trie. So basically, if you look at it, you can also review the implementations for in the video for problem 208. Basically, a trie will have, let's see, you have some class called trie, and then we have some initializer, right? So you can write it like this, something, and it will have some methods. So for full-fledged trie, basically you have insert, right? You can insert a word, right? And also you have something, let's say, check its word, all right? So search word, let's see, search. Given the word, you can search if the word is in the trie or not. And also you can do search prefix, right? You can see, let's see, right, like this is prefix. You can have a prefix, it's also string, and you do a boolean, right? So this is basically it's a trie data structure and its functionalities. So here actually we don't need to do search, right, or search words or search prefix. We just need to implement the insert method, right? So with that said, let's do this. Our plan will be the following. First, we want to build the data structure that is suitable to the current problem, and then we just apply the functionalities we get after we implementing the trie data structure. So that will be actually very easy. As for the main code, it will be 1 line or 2. So within this solution class, I mean. So here I'm going to follow this video for 208 to implement a trie that is suitable or adapted to the current problem. So here I'm going to have a trie node. So I'm just write a initializer, right? So self. So the reason that I choose to use a trie node, I just want to emphasize the trie node. The trie is n-ary tree. In some sense, it's a recursive data structure, right? So we have self children. Let's see, it's a dictionary. So also we want to have some counter, right, as suggested here. So we want to see n matches. So it's both a prefix and a suffix, right? So during the notice that when we do the insertion of words to the trie, we are going to start from left to right. So we are going to naturally maintain this order, right? So here we are going to set it to be 0 at the very beginning. So now let's implement a trie data structure. So class trie. So first let's do an initialization, right? So self. So then I'm going to make it a root is trie node, right? So notice this current counting for the trie node. So this self root, because it's a trie node object, it has 2 attributes or field at least. So that is children, and the other is n matches. Currently n matches 0, right? So next I'm going to do a insertion. I'm going to do an add. So this is in parallel to this insertion. So we want to insert a string or a word. So here I'm going to use a string to adapt to this problem. You can think of this add as the insertion and this s as a word in the video for problem 208. And then first, the current matches, we want to do the count. so it's 0, right? So because so this number will measure adding this current string, how many pairs we can get. For example, if you just originally you have a, adding this one, you are going to produce the index 0 and 1. This is the one pair. And then if you add this one, you're going to produce 2 pairs. One prefix and suffix is a, and another one is aba, right? So in other words, adding this one will produce 2 pairs. Adding this aba, well, it will produce 1. And adding this one will produce 1 because it's corresponding to this one. So that's our overall thoughts. So this matches will measure. So if you add a string from left to right, how many pairs added or yield. So then the current node will be self-root. And then we just need to continue. So what we do actually is this. For key in zip, because I want to compare both a and both the prefix and suffix. And then the thing is that we can do s and reversed s, right? So you can do this if you like. So this way, for example, if I do this a, so I can consider a and a. For this, when I look at the b, so I also look at b. But here, ab and ab. So what I want to use as a key is nothing. It's not the a single character, but a pair. So prefix part and the suffix part. So basically, this will be the pairs, right? For example, if you have AB and then the reverse will be BA, then this zip will yield 2 pairs. One is AB and the other is BA, right? So this line is to help you understand the zip function. So this S and this double colon and the inverse -1 is reverse S. So now we want to check the key. If key not in node, we can access its children attribute. Then what we do, we node children. So we set this key to be a trie node. And then we set our root to be the current level. In other words, this one, right? So we're going to set node to be node children key, right? So then also we want to, once you have this one, so then we are going to set the matches. It's incremented by node n matches. So n matches will be a attribute for this one, which is the counter in the hint, right? So then once we do this, because this matches, as we do this, we will return this one. So overall, we will return. So in other words, this add method within this trie class will do this 2 things. First, we add the prefix and the suffix pairs into the trie, and also we count before this index, because the corresponding index for s, how many pairs we can form. So this is the n matches. So because for each one we have this matches. This matches will be so for example, it will be count the current one. It will be node. After we finish the insertion, we're going to increment this in matches by 1, right? So this, let me explain again. So this n matches attribute will see how many it can match. So we increment by 1. For example, originally 0 and then it's the 1. Then you will get, when you do this one, you'll see, oh, I'm going to get 2, right? So this 2 will correspond to this variable. So this is the major functionality. So with that done, now let's look at the problem solution. So this is basically a true line, right? So what we do is that, so we can initialize this trie like this. So this is the straightforward. And then we just need to do the add or insertion operation. So basically, we want to, so because you have a result, this is a counting, right? Then basically what you do for s in words, right? So you do add, right? So, but the add will return something. So basically, what we do is let's call this try add method and this s. So this will return the increment. Then we result increment this one, and then finally we return the result. So this is the way of writing, but we write 5 lines of code. So before we digest deeper, let's first do a test to see if this code works. Our channel has n matches. Do you mean in MTCH? So n matches. Let's run this one. Yeah, it passes the first example. So now let's look at the generic case. Yeah, it passes all the generic cases. So I want to make 2 comments. First, let's just make it very short, make it compact. So what we can do is we can use comprehension. So we can do try add this word or s for s in words. So this will do the job. So you can see we do a submit. This will pass all the cases. So you might be doubt. So how do we understand this one? You can do some printing so that you can understand that. We can use this first example, and then you can draw the picture and do aid you digest the coding. But if you want to have some direct feeling, we can do some printing, right? So let's see, adding current word cs. So now let's call get 2 pieces of information. Node n matches. So this will be something like say node n matches. And then also we want to get another piece of information, that is returned variable matches. So this will be, let's see, matches. Right. So let's run this code again. Right. So when you add this a, right, so node afterwards the attribute is incremented by 1, right? Because you can see we increment this by 1, and then the returned match is 0. The reason it's 0 because there's no previous indices. So this is the adding the word a. So now you add aba, right? So the n matches is again 1 because after we do the insertion, we adjust its attribute value, and then because when in the process we call this node matches in the for loop. For this a, it has a attribute 1, so it returns matches 1. The reason is that for the index 1, it can form a pair with index 0. In other words, the pair is 0 and 1. And now you look at this one. So we add AB, ABA. So in this case, first it produced 2 matches. This corresponds to this index 0 and index 1. And then after we add that, and then the n matches is to be set to be 1. So this is the adding AB, ABA. Now if we add the last one, that is double A, right? So we afterwards we set its attribute to be 1, and then the matches it produces by adding this one is 1. Actually, it's corresponding to the index 0. In other words, index 0 and index 3. So if you sum all of those, so you get 0 plus 1 plus 2 plus 1. That is 4. This is this number. So you can also see the example 2. You can test example 2. And then, right, so you add this one. So after we add, its attribute is 1, and it yields matches 0. And then you add this one, and it yields matches 1, because PA is both a prefix and also a suffix of this PA. So in other words, 0 and 1 form a pair. And if you add MA, so after we do the insertion, this node will have a the last one, so the corresponding to A will have attribute value 1, but it yield matches 0. And for this one, it will yield matches 1. It actually corresponds to index 2. So in other words, index 2 and 3 form a pair. So if you do the summation, it will be true. So that's corresponding to this number, right? So with that said, I guess we finished the coding part for this problem. I would say this problem is marked hard by LeetCode. And if you have some good feeling or intuition with the Trie data structure, and then you do a partial implementation of the Trie and take the current problem logic into the insertion or add method, then writing the solution will be not that hard, I would say. So with that said, thank you for watching.